Sylvain, can you hear me?
Yeah.
You can start.
Perfect. Thank you. So good morning, good afternoon, and good evening, everyone, depending on where you are connected. My name is Sylvain Chazot. I'm the sales director of Altair France, and I'm very pleased to welcome you to this Altair conference as part of the GEC Composite Conference. So as I mentioned, we are pleased to have you everyone here today to discuss about composites and composite simulation and composite design and certification. We have been working with GEC for many years, and we are holding this conference as part of the GEC Connect. So let me first introduce the agenda. I will do a short introduction on Altair before we go into a presentation. So one will be from Altair on our composite solutions, and then we have three speakers from three companies. One KTM E-Technologies, then we have SNCF and CDTech, who have accepted, to give presentations during this Altair conference, and I would like to thank them all for their participations. So, and we will close with panel discussions with some of our speakers, and also including technical experts from Altair. So each presentation will be roughly about 20 minutes, and then at the end we'll have this panel discussion. So let me go first into to give you a few words about Altair for those who don't know us. So Altair's vision is to help customers drive decision, leveraging simulation, high-performance computing, and artificial intelligence. So these are the three main pillars of Altair's, and this is how we see the future is a mixture, convergence really of simulation, HPC, and artificial intelligence. We are one of the leaders in the software vendor world. We've been here for, I would say, more than 30 years in this industry, and about 3,000 people working at Altair, engineers, scientists, and creative thinkers. We have put a lot of effort in also having local support worldwide. So we have 86 offices in 25 countries, and we are very proud of having 11,000 customers globally. So we have a lot of credibility in that space, and I hope that this presentation will show what we are offering for composites for the composite community. Overall, we do about $500 million revenue each year, and we offer more than 150 plus software products. So what makes Altair today, and why our customers are choosing us? I'm not going to go into details of all these 6 points, but maybe to highlight that we are best in class in data analytics, AI, and stream data visualizations. So for composites, we have also global domain and simulation expertise with experts, in composites. We are not only software vendor, but also we have a very strong know-how in composite design and composite development and in composite manufacturing. We are optimization technology leaders and leader also in HPC technology. We are proud also to have open architecture solution. So our customers, they can really rely on our tools, to open and be interactive with other tools, CAD tools or other simulation tools. And also our unique licensing model is part of one of our main differentiators, and we offer third-party application through our licensing model. So our solutions portfolio is broad and vast at the moment. We offer things from the Internet of Things to data analytics, to design and visualizations. Today, we will very focus on physics simulation, dedicated for composite analysis. And for this, we cover a broad range of composite solution, from advanced material modeling to composite design certification, we offer a full solution, and that will be detailed during the presentation of our VP just after my talk, to show you how we can, help you to be more efficient in composite design and composite simulation. And finally, just before introducing the first speaker, we have our own full complete solution for composite design. We also offer a third-party product that are completing our offer, I would say, for composites. And here on this slide, you have some that can be relevant for you. So we have VABS, KitTex, CETIM, LMAT, and also part engineering that offer specific tools complementary to our offering. So thank you for joining today. This was a very quick introduction to this conference. I hope you will enjoy all the talks. And let me first introduce the first speaker. Jeff Roslager has a Bachelor of Science in Civil Engineering with a specialization in structures from Purdue University. He then received his Master of Science in Mechanical Engineering from Washington University in 2002. He worked for Boeing doing some research specific on composite activities, and he joined Altair in 2005. Now Jeff is currently our VP of Composite Technology at Altair Engineering, and he's helping industry customers to implement multi-scale material modeling, design optimization, and design certification technology into the current and future composite design projects. Jeff is also an affiliate associate professor at the University of Washington, teaching composite design and additive manufacturing. So please welcome Jeff and enjoy the presentation. Thank you.
Good morning, afternoon, evening, wherever you may find yourself in the world today. Hope everyone is doing well. I'm coming to you from rainy Seattle, Washington. My name is Jeff Roslager. I am the VP of Composite Technology at Altair. I'd like to take a moment to discuss with you today the Composite Solutions Team vision and roadmap. So the Composite Solutions Team primary objective is to provide composite solutions across the entire Altair product suite, really connecting all the Altair products, trying to provide intuitive workflows using the absolute latest of composite technology. So we're guided to achieve this statement through what I call the Composite Solutions Design Pyramid. This pyramid describes four main areas of development that we're actively working. The first and foremost and the absolute foundation of that pyramid is advanced material model development, where we're working on creating highly predictive material models while we're additionally retaining computational efficiency. The next development block that we're working on is integrated manufacturing and structural simulation, where the goal there is to be able to use the manufacturing simulation information, principally fiber orientations and residuals, in a structural simulation in order to improve the predictive accuracy of the structural simulation models that we're building. Also to do that, build those models with some amount of efficiency. Of course, Altair has always been a leader in optimization technologies. That isn't going to change, and we continue to focus on that even within our Composite Solutions team. What we're really doing is bringing those fundamental composite technologies into the composites world, and even extending some of those technologies. And I think you'll see that we're going to offer a very unique composite design optimization methodology that produces some really interesting composite designs much quicker than traditional methods would allow you to do. And then last but not least, in our design certification development block, it's all about producing a FEA integrated composite stress toolbox in order to do traditional or classical composite calculations that you would use with your certifying agency in order to substantiate a design that you may have. So let's talk a little bit about each of these blocks in slightly more detail. So in the advanced material model development block, it's really all about transitioning from a homogeneous isotropic world to a heterogeneous anisotropic world, and really becoming as comfortable with heterogeneous anisotropic material models as we are with homogeneous isotropic material models. And we're focusing on three main product forms right now. In the continuous reinforced product world, mostly on unidirectional and woven product forms. So within those two product forms, the unique capability is actually the ability to bridge the scales from the homogeneous ply level to the constituent fiber and matrix level, and the ability to do that computationally efficiently and to obtain results at the constituent fiber and matrix level such that we can obtain significantly more accurate material models. Same thing in the discontinuous reinforced product world, which really is focusing on the reinforced injection molded material world, where we're doing the same thing, where we're describing the heterogeneous anisotropic nature of these materials, characterizing that heterogeneous anisotropic nature, and accurately and computationally efficiently developing material models to describe all of that for you. So at the end of the day, it's all about reducing the time and cost in the design process due to incomplete material understanding, or not even incomplete, an inability to highly accurately model these materials, and bringing that to the forefront. It's also about reducing the amount of experimental data required to build these models, not necessarily bringing that to zero, but absolutely reducing what's required in order to develop these highly accurate material models. And of course, being able to increase simulation accuracy while we're doing all that and maintaining computational efficiency. The product, the principal product that we're using inside of the advanced material model development block is what we call Altair Multi-Scale Designer. What's really unique about this product is that it allows for the exact same material models to be used within all commercial solvers, implicit and explicit solvers included. And of course, it's very tightly integrated into our own solvers, OptiStruct and Radios. But the exact same material models are also available in other commercially available commercial solvers out there. It is indeed exactly the same material model and exactly the same code. We are using that through the user material capabilities of all of the codes, which is quite a nice thing to be able to do. When we're talking about integrated manufacturing and structural simulation, again, it's all about being able to efficiently build these structural simulation models while we're bringing information from the manufacturing simulation into that structural simulation in order to improve our predictive accuracy of these structural simulation models. Three main areas that we're focused on. So in the area of traditional or automated layup and infusion methods, we're working on integrating draping simulations for obtaining fiber orientations and or residuals into the structural simulation very quickly and efficiently. In the injection molding world, mostly the reinforced injection molding world, but also unreinforced injection molding, we're working on, again, bringing the fiber orientations and the residuals, whether that be thermal gradients and even using those thermal gradients to understand warpage and residual stresses and strains into the structural simulation world so that we can, again, improve the accuracy of those structural simulation models. And the third area we're working on is filament winding, quite a bit of composite pressure vessels, or CPVs, where we're using filament or winding simulation software, which again is providing us fiber orientations and or residuals of various natures that we can bring into the structural simulation world and apply those to improve, again, the accuracy of those structural simulation models. While we're improving the accuracy, we want to be able to do that efficiently. You're going to notice that quite a bit of what we do is about efficiency and doing things as quickly as possible. A good example of a complete workflow in the integrated manufacturing and structural simulation world is the Altair injection molding solution workflow. It involves three main pieces. So we have just released Inspire Mold, which is a fantastic molding simulation product. It allows you to do your fill, your pack, and your cool simulations. In addition to all that, you can get your fiber orientations after you do a filling simulation. Multi-Scale Designer is used in concert with the molding simulation to develop a heterogeneous anisotropic material model for that particular reinforced injection molded material. And then we bring both of those informations together into the pre and post processing world, which is HyperMesh and HyperView. HyperMesh, where we build the structural simulation model. HyperView, where we're post processing that particular structural simulation model. And of course, we're using OptiStruct in order to perform the solution, whether it's a solution of a warping simulation or whether it's a strength simulation, including warp residuals in that strength simulation for ultimate load carrying capability. So it is quite an advanced, wholly contained. I think what's really unique about this particular solution workflow is that it's wholly contained from all the way from the beginning to the end within the Altair product suite. Really solving the interoperability problem that you might have to go through if you were going to a la carte the pieces of this together from other commercially available offerings. Okay, going into composite design optimization. So again, using traditional capabilities in the concept design optimization world, namely topology optimization, which is going to give us in the composite design optimization world our part shape. We're using that exact same technology to really tell us what should the part shape be. But we need to go a little further with composites. So once we know that we have a certain part shape, we can make up that part shape with any number of composite plies and any number of orientations and thicknesses that we need. And so we've extended our optimization capabilities into two primary technologies. The first one in the composite concept design optimization world, which is called composite free size optimization. And that technology is really focused on trying to describe what are the most efficient ply shapes. You're going to see here I have a slide that shows that we're actually synthesizing, just like topology is synthesizing a structure, we're actually synthesizing ply shapes that make up that structure with that particular concept design optimization technology. Once you've kind of interpreted your concepts, then we can get into the detailed composite design optimization phase. And there we're talking about a technology called composite size and shape optimization. It's equivalent to the size and shape optimization. You know, we just put the word composite on front because we're talking about sizing ply shapes now. And so it's going to principally answer the question, well, how many of each ply shape do I need to meet my engineering targets or my engineering requirements in terms of, you know, no fiber breakage, no buckling, you know, maybe certain deflections and whatnot. So bringing those engineering requirements in. We're also really focused on bringing in repeat laminate technology and double-double laminates. You may have heard these things from Steve Sives' group at Stanford University. So we are bringing those technologies, which are fantastic technologies, into this design methodology, and you're going to start seeing these the ability to optimize with these double-double laminates, which are just you know, theta minus theta, phi minus phi, ns type laminates, where we're really optimizing on what is n, the number of repeats, and what are theta and phi, what are the angles in this double-double laminate. So using our optimization technologies to solve for that. Hopefully I can show you the image here where the real difference in this unique aspect of the composite design technologies, optimization technologies that we're bringing to the commercial world is the ability to synthesize these ply shapes. Shapes that you might not have intuitively thought to make before, but absolutely are valid and can be made. You can see some examples of some ply shapes here that, again, might not be super intuitive, but absolutely are reasonable and practical to be able to manufacture. So while we're synthesizing these ply shapes, we're also optimizing the ply angles and the ply thicknesses And really, we're providing a modern, robust composite design methodology that is quite different than traditional design methodologies in the world of composites. So last but not least, in our development block of design certification, it's all about integrating composite stress toolboxes into a finite element architecture world. And that's always been kind of the outstanding item of these stress toolboxes, which exist in numbers across many, many companies, is really interoperating with the finite element architecture or finite element information. And so we have a unique opportunity in Altair since we acquired ESAComp, which is a fantastic composite stress toolbox that came out of ESA in Europe, the European Space Agency, where we have acquired that technology now. And what we're working on is really providing an integrated version of that technology inside the HyperWorks framework. And so really solving the interoperability problem, the exchanging of information between your finite element models and your traditional composite sizing calculations or certification calculations in order to really reduce the pain point there. So that's all about FEA Integrated Stress Toolbox. It is going to provide capabilities for composite beams, panels, bonded and bolted joints for both design and analysis. It can handle linear static, nonlinear, buckling, first ply failure, even progressive failure of laminated structures. And it's quite exciting to see this technology come in. So by and large, those are the four main areas that we're focused on in developing. Hopefully this gives you some insight into the vision and the roadmap and where we're going. The team was developed and put together just about a year and a half ago now. You should start seeing the fruits of our labor coming in with version 2020 and beyond. I hope you enjoy it.
Thank you, Jeff, for this complete and comprehensive overview of the Altair solutions and the composite solutions that we offer. If you have any questions for Altair, don't hesitate. We have a virtual booth at the JEC, and you can connect and ask questions, to our experts if you have any question of what you've just seen. Let me introduce now our second speaker. So our second speaker is Dr. Engineer Martin Perterer. He's the head of simulation at KTM E-Technologies. So Martin studied aerospace engineering at the Technical University of Munich in 2007. Then he was research associate at the chair of lightweight structures, also at the Technical University of Munich. He did a dissertation on the damage identification and evaluation of CFRP structures using phase modulated thermography. And then he joined KTM Technologies in Salzburg, Austria, as a manager of simulation and research. And since 2020, he is now the head of simulation at KTM. So please welcome Martin. Thank you.
Hello, ladies and gentlemen. My name is Martin Perterer. I'm responsible within KTM E-Technologies for all simulation topics. Today, I want to present you some insights into simulation topics for the development of innovative lightweight vehicle concepts. Here, I want to focus especially on the role of Altair products in this progress. KTM Technologies is a company within the Pierer Mobility AG dedicated to the development of new vehicle concepts, and here especially electric powered vehicles. Regarding the simulation, we are focusing on a lot of different simulation techniques, starting from static simulations at the early product phase for concept development and comparison, up to dynamic simulations and crash simulations, We're doing aerodynamic assessment using CFD simulations. We're including also the manufacturing process in the development and also in the simulation. We have here process simulation techniques as we're focusing on electric concepts. We are also focusing on the dedicated simulation topics and tools regarding electric motor, battery, and range simulation, for example. And we combine everything with optimization techniques. Today I want to present you 3 case studies. The first one is the MotoGP fairing, or the development of the fairing for the MotoGP motorcycle. The goal of this development was to provide a very fast and efficient way of developing new fairing components that can be quickly tested on a test track. Therefore, in the first step, we are asking the driver where the issue comes from. So where he loses time, for example, when braking, when accelerating, in the turn, when going at maximum speed. And then we're trying to set up appropriate simulation models, especially focusing his needs. We have to define whether it's a global problem, either the whole fairing has to be changed, or it's some kind of local problem where some additional aerodynamic elements, for example the G-wing, is a possible solution. We also have to define appropriate targets for our joint optimization. Either we want to maximum the downforce or minimum the drag, or whether we want to influence the flow around the driver or the force acting on the driver. In order to be quick on a test track, we need some appropriate manufacturing techniques. We think that additive manufacturing in combination with simulation is a very good tool to do so. And here we need especially simulation topics to define the back structure below our aerodynamic surfaces, to give the part enough stiffness that it will not deform during the ride. And here, as you can see on the slide, we developed lattice structure that differ in the lattice itself, the density of the mesh, and also the size of the structure. To summarize this whole process, with the combination of Altair simulation tools and appropriate manufacturing techniques, we are able to really quickly get from an idea of improvement to a part that can be tested on the track. We can tailor it to the needs of the driver, and we even can do different parts for every single driver without major additional effort. And what is also a very good part of it is that compared to conventional CFRP solutions or the approach here, we do not need, for example, molds, and also we do not need the expensive CFRP material. And so the whole process is not just faster than CFRP, but also a lot cheaper. The next case study I want to present is the development of a vehicle frame within a new urban concept. This new urban concept or the platform is called Emotion. Emotion is a research project where the goal is to develop a cost-effective, energy-efficient and comfortable new light electric vehicle platform, especially tailored for young and older generation, where the platform provides the possibility to be able to place vehicles in different categories, for example, the L1 and the L3 category. We have 3 different areas of interest. where the first one focuses the lightweight frame design and packaging. This is what I also want to focus in this speech. The other two are electric efficient powertrain and an innovative user-centered HMI. On the right side of the slide, you can see a graphic that further goes into detail here by providing some targets. You can see here that a lot of different targets are defined within the project. Mass targets, energy densities for the battery, efficiency targets, and there is a strong connection or an influence from one target to the other. For example, the mass is influenced by the battery size. The battery size influences the range. The structure is influenced, etc., etc. And therefore, multidisciplinary optimization methods are necessary in order to find a global optimum. To do so, we went through different steps. First of all, we wanted to get realistic load data for this new vehicle concept. Therefore, we set up a load data acquisition vehicle, which is somehow representative by means of stiffness and by means of weight for the vehicle platform we want to develop. We then applied this vehicle or the vehicle components with measurement equipment, with strain gauges, for example, calibrated on a test bench, and then went riding with it on a test track and also on real scenarios, as you can see on the slide. We used the simulation technique here mainly to define positions for the measurement sensors to be just sensitive, for example, to a single force here, that we can divide the different forces in a right way to then come out with load collectives that we can use for the further development of the bike and also for further test bench investigations. In the next step, we try to include in our optimization some kind of implicit know-how, or in other words, we want to include the user at a very early stage in the development. We thought the ergonomics as a very important input here. This is the reason why we set up an ergonomic bike, where we then collected the impressions from the users. As you can see here on the top, we combined this investigation with packaging investigations to place the main components, battery, motor, etc. We combined it also with first simulations regarding the topology of the frame in order to identify load path, to see whether there is feasible solutions to put a frame somewhere or there is no space, etc. And at the end, we tried to collect all input with some kind of parameters or formulas to be then included in the optimization method. On this slide, you can see some results from the topology optimization. We used this simulation technique in order to play a little bit with different manufacturing techniques, with masses, stiffnesses, materials, etc. And then there is a typical graphic coming out of it on top and the bottom on the left side. So it's a kind of density distribution. And then we derived out of this a technical sketch in the first place in order to interpret those solutions with some possible structure. You can also see here different battery concepts that also influence the structure here. So the output here mainly is to have a first idea how this looks like. In the next step, we set up step by step a 3D CAD model for the main structure, where we also used simulation techniques for the development or the detailation of this structure. So here we set up a SimSolid model, which is a meshless simulation technique that is more or less real time. And so we were able to support the CAD engineers with important decisions. And then on the bottom, you can see the final CAD, or the simulation of the final CAD, which is then the starting point. Further optimization, this multidisciplinary optimization, where we parameterized the structure, the thicknesses, wall thicknesses, positions of the pipes, materials, etc., etc. And we combine them with economical targets, let's say costs, and also with the CO2 footprint to find a global optimum for our structure. The project Emotion is going on at the moment. The development is also ongoing here, and the first prototypes will be set up by the end of this year. The last thing I want to focus is a series part that we try to rethink by using simulation techniques. So this is the, we call it a new generation footrest. Here we took a standard off-the-shelf KTM footrest from the KTM Super Duke 1290R. You can see the bike on the top and the footrest and all parts of it below. And we wanted to use simulation techniques in order to rethink this structure, where we want to keep the stiffness equivalent as it is right now. We want to reduce weight, and we also want to incorporate some new design aspects, or let's say new design ideas. Here in this case study, I want to focus a little bit more in depth on the simulation approach here. You can see here on the slide two different pictures. On the left hand side there is you can see the design space we defined. We want to develop mainly the footrest main plate. And on the right hand side you can see some non-design spaces where we want to keep the fixation points as they are, and also integrate the existing components into the optimization. We went in 3 steps here, and we tried to also then compare those 3 different complex optimization strategies. The first strategy is let's say a standard optimization with nominal values, which then results in a first design proposal. The next step is to include scattering and to define a design of a pyramid experiments, where we then get out some different designs with scattered loads, for example, or scattered material parameters. And then we combined all this output in order to generate a second possible design. And then in the last step, we focused on the worst case load cases, and also included probabilistic to then finally come up with a robust design proposal. Here in this slide you can see some results of the full factorial design of experiment. You can see here on top that if we are varying the force and materials and other things, we come up with different load paths. So there is a need to cluster those load paths, which we did here by using several colors. You can also see here on the bottom that we did here some sensitivity analysis in order to define the important parameters here, where the lines that, or the parameters that show a very horizontal line have not real influence on the properties of the part, and those with a very steep or vertical line from minimum to maximum have a very intense influence on some property of the structure. And then finally, here's some impressions or an overview of the robust design assessment. You can see here in the picture that although a footrest is rather a simple part, there is a lot of deviation in forces, for example, from the position where the foot is set on. It depends on the shoe size, it depends on the driving status or the driving condition, it depends on the ability of the driver, how to drive. So it's not that easy to reduce the load cases to a single force, let's say. And so we included this different load positions, these different load directions, combine it with probability. You can see here on the top right where there is some expression for this to the last optimization step to then get out a robust design. You can see here this result on the top right hand side, where on the top left hand side there is the series part. And we have now two different ways of generating 3D data out of it. There is the direct 3D generation, where we can either use surface data directly by post-processing in HyperMesh, or we can use faceted data. Then we have to go through some kind of smoothing algorithm or geometric wrap to come to the CAD data, or we go an indirect way where we export the faceted data into a CAD program, CATIA for example, and then set up a generic parametric CAD model, where we are then also able to simplify the structure a little bit and also include some other inputs. On the top picture on the right side, on the bottom picture of the right side, there is an interpretation of our design company Kiska based on the results of the topology optimization. To conclude my talk, I hope I gave you a short insight into different simulation topics, into different ways we're using the Altair simulation portfolio. For us at KTM Technologies, it's very important that we have a fast and reliable simulation processes, and we try to use them at a very early stage in development to overcome uncertainties and to already use facts for the decision of the way forward. And what we also include very early is not only technical issues, but also costs or some kind of engineering complexity and implicit user know-how. Thanks very much for your attention.
Thank you, Martin, for these very interesting examples on how to use simulation technologies to optimize process development. Now, I will introduce our next talk from SNCF on using FEA for train homologation. So we have three speakers on this session. So Patrick Jumin is currently the National Technical Referent for car-body shell structures and interface at SNCF. He has a PhD in civil engineering from the solid mechanics laboratory from École Polytechnique in France, and the Master of Science CAD, CAM, and CAE from Cranfield University. He's also a SNCF expert for car-body structure and interface, and SNCF BNF expert as SNCF leaders of European research project on the car-body structures and passive safety domains. Our second speaker from SNCF is Karim Slimani. He is a composite expert and mechanical engineer for car-body structure. He's got a mechanical engineering degree from INSA Val de Loire, and he's done some mechanical research and development from master's degree of University of Poitiers. And then we have Derek Joel Kang Tapshon. Sorry if I misread the name. He's a mechanical engineer specialized in finite element analysis on static and dynamic calculations. So all the FEA dimensioning and optimization of the body structures for train acquisition, renovation, and maintenance projects. So let me welcome SNCF and our 3 speakers now and enjoy the presentation. Thank you.
Hello everyone. Today we are going to talk about the virtual homologation dedicated to the rolling stock's car body structure of the SNCF, the French railway operator. After a short introduction on our function, I would like to present you the current state on car body structures virtual homologation approach in the railway industry. My colleagues will show you the current developments with the application to the bolted assemblies design, the composites design, the topological optimization, and finally, I will sum up in the conclusion what will be said in the presentation. We work in the engineering center of the rolling stock of the SNCF. We are in charge of the acquisition and the modification of the French trains. This takes us to often used numerical simulation as it can be applied for maintenance support and for actions in research projects, European and national. For the static, fatigue, and passive safety analysis, we have a good experience and proven methods with the use of European standard, EN 12663 for static and fatigue, and EN 15227 for passive safety. In our static and fatigue analysis, we start from a CAD model using a CATIA software. After, we prepare our simulation model under Hypermesh and calculate the reference loading cases. We have a recent changeover from ANSYS to OptiStruct software in order to simplify and optimize our licenses and to limit the tools with the HyperWorks environment. Use test calibration to validate our numerical model is really essential. For equipment setting up on the car body, we have the possibility to apply the CATIA modules for a simple approach. But when the modeling is too complex, the action is the same as for the car body structures. On the figures, you can see the establishment of a technical rack in a TGV power car with the simplified model for the rack and the calculation of the support and the fixings. For passive safety, we apply radio software since the 90s with a proven combined method using tests, calibration of the tests, and numerical simulation of the reference scenarios. This method is well described in the 15227 standard. We have specific applications like animals impact studies with severe consequences on our trains and the need to protect our antenna and other safety equipment. On the figures, you can see the protection of 4 braking systems. Also, biomechanics is well developed in automotive industry and in railway for the States or UK, for example. Further efforts needs to be made to require biomechanical studies for new rolling stock, mainly for abdominal impacts, with the necessary development of adapted tools and criteria.
Hi everyone, I will present you the design of composite part on use cases. The first challenge for the design of composite is to make consistency tests on calculations. When it is done, we compare non-linear and linear calculation to know if linear calculation with OptiSo is conservative or not. When we are confident with the calculations, it is possible to design composite or redesign composite, especially when you have a negative feedback of composite's behavior during commercial service and it is not possible to modify the part. We will see an example further. Also, when there is a negative feedback with the composite part, but it is possible to modify, it is necessary to design the modified part and quantify the gain associated. At the end, the design structural composites parts allow us to control the work design done by terrain manufacturers and homologate new generations of train with composite structural parts. At the beginning, it is necessary to obtain some parameters of the composite like Young modulus in fiber direction and so on. We obtain it for polyester glass used on train fairing. One of the tests we wanted to correlate is traction test. With that, it was possible to adjust non-linear parameters. The same was done with 4-point flexural test. Then we wanted to know if OptiStruct calculation we can obtain conservative results compared to nonlinear calculation with radius. We also want calculation as quick as possible. For that, we use a bougie hatch used in per-ribbon train, as we can see here. This his localization is for the part is close to the bogie. We put in the calculation to 200 Pascal pressure, maximal pressure seen by this train. It is put on external surface, as we can see here, and we use material card, two type material cards for the ply, matte and taffeta. The composite is made of 2 point insert and 1 lock point below. The result of the comparison is shown in this slide. As we can see, concerning the displacement, it is different because of the decrease of mechanical characteristic with nonlinear behavior of the composite compared to the linear calculation with OptiStruct. It introduces more flexibility. However, concerning the CIU index in OptiStruct calculation is above CIU index radius calculation. We can conclude that using OptiStruct is okay and faster than radius. Now I will show you a different example of negative feedback. For the suburban train from Siemens, we had some problem because the part was done by pultrusion process. As we can see, the hatch is maintained by composite slide in red, but some cracks appeared, as we can see here. The pultrusion process with only one fiber direction is not adapted to the direction of the solicitation. Another example with negative feedback is air conditioning hatches, as we can see here. We had some unwanted hatch opening during commercial service. There is too much flexibility and not quantification of effort in the insert. We will see the necessity to modify the air conditioning hatches and estimate again further. As we are confident with the parameters, it is easily possible to design composite on suburban train next new generation, for example. We modify it by introducing foam in this place to improve the stiffness of the hatches. We add also over-lamination on the foam on in the insert in the yellow. The aim was to reduce the displacement when the part is under aerodynamic pressure. Also reduce CIU index and at the end estimate the traction and shear force on the insert not done by manufacturers. At the end, all it's okay. Displacement, CIU index and force. For another suburban train, as we can see here, it was necessary to reason all the parts. So we decided to create new geometry, a new insert, and estimate CIU index force in the insert. Everything is okay. Also, for the structural part, we participate on shift-to-rail pivot project, which consists in developing the conceptual detail design of the different demonstrator to be performed together with the all rotated manufacturer activities needed to build the physical specimen. For us, design composite permits to know the necessary and sufficient element to homologate structural composite parts in a train in the future to be able to maintain a composite structure during the entire life. Thank you very much for the attention. I will let my colleagues speak for the other items. Thank you.
I would like to shift focus now to the topological optimization that is fundamental today for new design. Indeed, we apply topological optimization for mass reduction that is essential for the reduction of the energy consumption of the required limited mass. We use also this tool for new manufacturing applications like 3D additive printing. The figure, resulting from a European research project, shows the methodology to optimize door and windows with the necessary reinforcement location. You can see the X shape for reinforcement element. As for the static and fatigue approach, we use the CATIA software for the CAD model, then HyperMesh to prepare the model, and OptiStruct for calculation. The topological optimization is particularly well adapted to the composite structures, with the well-known sentence, the right material in the right location. If you look up at the screen, you can see the distribution of the necessary fiber orientation along the car body structures. You could see where longitudinal fiber are necessary, vertical, transversal, and diagonal direction, but also when a classic isotropic material is more appropriate, like with the blue color. On this slide, you can see an example of topological optimization study. This study is about the cracks of wagon tension to carrier rails. The figure shows the initial volume for optimization, the optimized shape, and the corresponding calculation with the possible manufacturing elements. Here, a simple welded plate. This specific shape could be manufactured with 3D additive printing. We cannot show last elements manufactured with 3D additive printing for existing trains and the future rolling stock, but structural elements were tested in laboratory and are tested now in operation on our trains. This new method allows the use of more strength expansive materials than the classic ones, thanks to the base material reduction. As conclusion, virtual homologation is now broadly applied and mastered for the car body structure design in the railway domain for the static, fatigue, and passive safety analysis using the HyperWorks tools. Nevertheless, improvements are necessary for bolted assembly design, composite designs, and also biomechanical studies. For future, it will be necessary to master the topological optimization and to combine numerically the track and rolling stock interaction. Thank you for your attention.
So thank you, SNCF, for this great presentation on how to use simulation techniques for car body development for train. And now our last talk for the Altair conference is from CD Tech. And I would like to introduce Nerea Marquet. She has a degree in chemical engineering and has been researching in the field of composites since 1990. So in 2013, she joined the group of polymers and composites in CD Tech. And currently, she works as a project manager, being research is aimed at the processing and characterization of composites with tailored properties. So Nerea Marquet is a polymers and composite expert, and she will talk about the epoxy, thermoformable, repairable, and bondable smart epoxy-based composites for aerostructures. So welcome, Nerea. Thank you.
Hi, good afternoon, everyone. First of all, I would like to thank Altair for giving me the opportunity to present the epoxy project and also to all who are attending this session. My name is Nerea Marcaide. I work in the Polymers and Composite Research area of CD Tech, and in this presentation, I will show the research that is being carried out in the epoxy project and how numerical simulation tools applied from the first stages of design can improve the quality of the final products as well as reduce material waste. So let's start. Firstly, I'm going to make a brief introduction to the project. Then I will present the technical approach and some of the results obtained. And finally, I will finish by exposing the main conclusions and next steps. Well, epoxy project is entitled as Thermoformable, Repairable, and Bondable Smart Epoxy-Based Composites for Aerostructures. The project is financed by the Horizon 2020 program within the topic focused on the maintaining industrial leadership in aeronautics. The proposal was presented and approved in 2017 and finally was started in September 2018 with an initial duration of 42 months. The consortium is composed by 11 partners from 6 European countries. IDEC, Eurecat, UNE and CDTech from Spain, Altair and Arctic from France, Sonaca & Co-Expert from Belgium, IVW from Germany, University of Ioannina from Greece, and Eire Composites from Ireland. The main objective of the project is to reduce the production and maintenance cost of composite parts in the aeronautics sector by developing and introducing 3R composites that are based on 3R resins. To explain what this resin consists of, firstly, I need to compare thermoplastic resins with thermoset resins. Well, thermoplastics are based on linear polymer chains that can be remelted when heating, while thermosets are based on cross-linked polymer chains that, once formed, remain in a permanent solid state. Due to this difference, thermoplastics can be reprocessable, recyclable, and soluble, but their chemical, thermal, and mechanical resistance is reduced. On the contrary, the thermosets can't be reprocessed or recycled, but they have better chemical, thermal, and mechanical properties. The epoxy resin approach in the epoxy project is based on a network that becomes dynamic when heating, but this dynamism doesn't affect the integrity of the network. This means that when the temperature is below the glass transition temperature of the resin, the network is static and the resin has the properties of the thermosets. But when the temperature is above the glass transition temperature, then the network becomes dynamic, and in this moment, the resin has a thermoplastic behavior. So we can say that the resin, the 3R resin, has the advantages of the thermosets in terms of chemical, thermal, and mechanical properties, and the advantages of thermoplastics in terms of processability, as the 3R resin is reprocessable, recyclable, repairable, and also weldable. This is possible by replacing in the 3R resin the amino hardener, typically used in the epoxy resins, by an aromatic disulfide hardener. The resin produced with this chemistry are called bitimers. Regarding the objectives, the project focuses mainly in 4 specific objectives. First, the development of 3R resin that meets the requirements of the aeronautical sector. Second, the development of 3R thermoforming process based on the 3R resin that allow high volume production processes faster and cheaper than the autoclave. Third, the development of 3R repair process that, combining with structural head monitoring technologies, allows early detection of the laminations or the bonds that can be repaired by easy and fast repair methods. And fourth, the development of 2 3R bonding processes, one based on the welding of 2 3R substrates that will be faster than conventional bonding processes, and one based on the conventional bonding process, using for that 3R adhesive that allow to increase the bond line robustness when bonding 3R substrates. As you can see in the technical approach in the slide, the work plan structure is divided in 8 work packages. Work package 2, 3, and 4 are related to the technical development of the 3R technologies to a TRL4. And work package 5 is related to the validation of the technologies in industrial environment to a TRL5. For that, 2 demonstrators were selected that will be manufactured and tested in the project. The first one is a subcomponent of a representative fan coil and is formed by a skin, a transverse stiffener, and a longitudinal stiffener. And the second one is a subcomponent of a representative leading edge, which is formed by a nose and 2 webs. All the technologies are supported by simulation methodologies that are being adapted to the 3R concepts. So, in the project, several materials and processes have been developed, which are summarized in this table. Simulation activities have been performed on thermoforming, adhesive bonding, and repair technologies. And today, I will focus on the simulation performed on thermoforming of laminates and enduring prepregs produced within the 3R resin. Okay, so firstly, the 3R resin was formulated, being its properties comparable to the properties of the traditional epoxy resins used for aeronautics. The characteristics of this resin that we have formulated in terms of viscosity and curing cycle were adjusted in order to be suitable for infusion and or resin transfer molding processes, directly to produce the final parts or to produce intermediate laminates that later will be used for thermoforming. The resin can be prepared and supplied in monocomponent or two-component version. Once formulated the resin, afterwards its thermoformability was validated, and for that, a resin plate fully cured with a TG of 170 degrees was successfully thermoformed at 200 degrees, as you can see in the picture. Once confirmed the thermoformability of the resin, a fully cured 3R laminates were produced using the resin transfer molding process. On the other hand, enduring prepreg was also produced. This prepreg is about the gel point of the resin. So this means that the prepreg can be stored at room temperature. Once produced the materials, the next step was to study different thermoforming strategies to be approached with the laminates and enduring prepregs produced with the 3R resin. For that, 3 different strategies were defined. The first strategy consists of thermoforming the fully cured 3R laminates in a discontinuous process, in a similar way to the thermoplastic organosheets. The second strategy consists of thermoforming a stack of enduring prepreg in a discontinuous process. During this process, the plies are consolidated and thermoformed at the same time. And the third strategy consists of thermoforming the enduring prepregs, but in this case, in a discontinuous process. In the process, in the first stage, the plies are pre-consolidated, and in the second stage are thermoformed, but the process is continuous. This option is suitable for the production of geometries with symmetrical sections like omega profiles. The image show that the proof of concept obtained by IVW during the development of the 3 strategies. I must say that at this moment, the 2 discontinuous processes are practically fixed, but in the case of the continuous process, it is being optimized. In parallel, it was developed the thermoforming simulation tool, and for that, 2 main research axes were developed. The first one is the ply-ply interaction modeling, which is a crucial tool to predict defects because local wrinkle or the cohesion can be predicted only if the interface behavior is simulated. It was proved that the cohesive element approach is able to capture the behavior of the 3R resin. In the case of the second modeling, the 3R laminates behavior, it was implemented a new material mode that on the one hand can capture the material anisotropy during forming process, and on the other hand can simulate nonlinear elastic behavior of the fibers and the contribution of the isotropic resin. For that, 2 different resins models were developed, one considering the resin as a viscoelastic material and the other considering the resin as an elastoplastic material. In both cases, it was confirmed that the models can capture the material behavior at different temperatures and strain rates. The material was calibrated using tensile bending and in-plane shear test, and the models were tested on structural scale models such as semi-spherocylinder and hemispherical models that you can see in the pictures. It was obtained a good agreement with real parts, and it was possible to predict with accuracy the final shape, type, and location of defects like wrinkles and delaminations. Next, the models were adapted to simulate the 2 elements that will be produced by thermoforming, the longitudinal stiffener of the fan coil demonstrator and the webs of the leading edge demonstrator. In the case of the webs, several material and process options were studied in order to define the parameters that better avoid wrinkles and delaminations. Based on the results obtained, it was defined the type, geometry, and holding system of the blank. The best results were obtained with a punch in 2 steps, combined with a V-shaped cut, being the depth without wrinkles of 10 millimeters. It was observed that the springs were not a good option, as they add much complexity without improving significantly the quality. In the case of the longitudinal stiffener, it was designed with omega shape in order to increase the torsional stiffness of the structure. It was included a little pan down, and the head was reinforced in order to carry the main tension and compression loads. Both geometries are usual in this type of stiffeners. The simulation tool was used to study the influence of the pan down and variable thickness on the quality of the thermoform longitudinal stiffener. It was observed that mostly the laminated areas appear close to interface between reinforced and not reinforced areas, but no wrinkles are expected at the end of the process, as the lamination shall disappear thanks to the repair capability of the 3R resin. Finally, the conclusions. So far, we can conclude that 2 numerical tools have been developed for the thermoforming of 3R laminates: the ply-ply interaction modeling based on cohesive element approach, and the 3R laminates material behavior based on viscoelastic and elastoplastic approaches. The models have been tested on structural scale models, and all of them show a good agreement between numerical simulation and test results. The models have been adapted to simulate the 2 elements to be thermoformed, the longitudinal stiffener and the webs. And finally, thermoforming strategy for the webs and head design for the longitudinal stiffener have been defined and confirmed according to the simulation results. The next steps are the production of demonstrators to validate the simulation results. At this moment, the molds are being produced, and we expect to have the first demonstrators produced by the end of this year. And this is all. Thank you very much for your attention. And if you have any questions, I will be very happy to answer you. Thank you.
Thank you very much, Nerea, from this for this presentation and for this application on the research side of composite design and simulation. I would like to thank all our speakers of today. Now we are going to end this this Altair conference with a roundtable, and I would like to welcome our presenters and also our technical experts on this session. So we have, I think we'll have in the room several people here. Okay, so let me just do a quick round and introduce each one of you. So we have Nera Makaide here. She just did the presentation from CDTech, and she's a polymers and composite expert. We have also Martin Perterer, who is the head of simulation at KTN Technology, and you saw also his presentation during the conference. We have Juan Pedro Ramirez, technical manager from Altair France. Also André Monique, program manager at Altair. Alessandro Amorese, application engineer at Altair, and also Francesco Russo, who is also application engineer at Altair. So thank you all for joining this this roundtable. The goal, obviously, for this roundtable is to share ideas, thoughts, trends, and discuss technical details. And I will start with the first question, general question, to try to set up also the context and on the general trends, in composite usage and application in your industry or your company. I will open the questions to our guest speakers of today, Nerea and Martin. So I'm not sure who would like to start. Maybe Nerea, if you want to answer this first question.
Yes, of course. I think that the epoxy project I have presented is a good example of the trends in composites and also the contribution that CDTech is making. Clearly, the composites market require more sustainable materials and more competitive processes. And we are working on it by developing a new generation of advanced composites based on dynamic covalent chemistry. And we are adapting them to the requirements of different sectors, such as aeronautics, as I have shown in the epoxy project, but also of other different sectors like automotive or wind energy.
Okay, thank you, Nerea. And Martin, what is your view on these trends in your industry?
I think we have to split it a little bit up because part of KTM Technologies that is involved in motorsports, there the trend is that the CFRP is still the way to go because of the extreme lightweight potential of this of the structures there. And on the other hand, for the serious products, it's rather difficult to include a big amount of CFRP in the structures. So the way forward I see it is to have some kind of multi-material mix, let's say, or hybrid structures where you just put CFRP locally in those areas where you really need it and include it or surround it with some cheaper material, let's say, in order to have a positive business case.
Okay, thank you, Martin. And maybe on the Altair side, a question to Andre. What are the new trends specific on composite simulation that you see as program manager at Altair?
Yeah, thanks, Stefan. I would say the majority of users is so much asking about like a specific method or anything to be implemented, like the latest composite fatigue laws or something like that. But it's rather really people are focusing on the workflows, like in-house workflows. And that's also where we have been focusing on. So to make those workflows more seamless and basically democratizing those tools that we offer for a wider audience as more and more engineers are actually working in the composites design world. So I think in Jeff's presentation, there were a lot of hints in coupling manufacturing simulation, the injection molding in there, draping, winding, all of those things. But also composite stress toolbox is a part of that. And lastly, maybe I have just recently read the term effective simulation as a trend in composites. That basically referred to all scales. So that brings me really back to the multi-scale modeling, which is an exception to the methods I mentioned at the very beginning. Because the multi-scale really made the leap from being an academic tool through like early adopters in industry to basically being a proven tool and now also being widely accessible to the users. And to close, maybe optimization is always there. It's been there a long time, but it's still a trend. Just because if you know the prices, you just need to save cost, and you need to get the material only where it's actually needed to get the performance out.
Yeah, and we saw several presentations on these optimization technologies.
Yeah,
so,
exactly.
Yeah, that's exactly a very good trend for the future as well. Yeah, thank you, Andre. And a question maybe for Juan Pedro. How Altair simulation to help you to improve the composite development process and specifically the manufacturing process? How do you see that?
How I see it, I think we have already seen that in the last presentation in the epoxy project. So as Andre said before, we work a lot of flows. So from the beginning to the end of the process design, and now one of the trends is how to take information of the manufacturing process and put that in our structural models. That may be fiber directions in short fiber injection or fiber direction when we are making thermoforming, okay, or draping something, and that we use that to introduce a correct stiffness, a correct global behavior of our structure. But if we are going more in detail, in order to predict defects, in order to see before the production starts if our process is producing correct parts, okay, we need to simulate that, and it's a very complex stuff, because we need to understand the process. We need to use advanced material models. So we have seen multi-scale. This is one thing, but in manufacturing we have also multi-physics, thermal behavior, phase change, non-orthogonal stuff, and so on. So we need to put a lot of technology inside, but if we are able to simulate that, as we see in the epoxy project, we're able to modify maybe the tools and the process itself in order to ensure the quality of the parts. And as you said, the optimization is everywhere. Sometimes we use optimization in order to determine where to put the composite, which direction, how much, thickness, and so on. But we can apply also optimization in the process itself. If we have a thermal dependent material, we control the temperature cycle in the process, the temperature dependency in the material. We can optimize the process, so make it shorter, ensure the quality of the parts, and maybe save time, save material, and ensure quality. So this is how I see the benefits of simulation and putting simulation in the manufacturing.
Okay, thank you very much, Juan Pedro. And talking about the challenges about this, maybe we can ask Nerea and Martin, what are the challenges they face regarding composite simulations and composite development? How, what are the future challenges that they're going to have to face for that? Maybe Nerea, if you want to.
Yes, well, in our case, in the case of our studies on the dynamic thermoset composites, the behavior of these materials when heating is very different to the behavior of the typical thermoset resins. So this is why, indeed, the material is thermoformable and also recyclable. So clearly we need simulation tools adapted to these characteristics that in the development phase where we are now at this moment can support the experimental studies. Firstly, to develop more robust materials and processes, and secondly, to reduce the design time and the time that we waste sometimes on trial error method. Yes, during this optimization process. So for us, it's crucial to have these simulation tools.
Okay, thank you, Nerea. And Martin, what is your view on that and the challenges that you face?
I think the main challenge here is, as I think we all agree here in this round, to use optimization in the right way to include every requirement we have. So in the past time, the main requirement was to be lightweight, but nowadays there are hardly any parts where we just have this target. So we have other targets like cost targets. We have also the CO2 footprint, for example, that is getting increasingly important nowadays. And we need some appropriate optimization tools that also include this partly implicit know-how to then be able to generate a structure that is lightweight, that is cheap, that has a low footprint, that is somehow adaptable for some platforms, as it is in cars. It's the same in motorcycles. So this is the real challenge, and when especially focusing on this CO2 footprint, also new materials come into play that
are, for example, natural fibers, etc., etc. And especially there, it's very important to have appropriate material data for simulation, not only static material data, but also dynamic data, crash data, to be able to introduce it in products.
Yeah, and exactly, and this is exactly the next question I wanted to ask to Francesco about how to get this real material data properties for the simulation, because these are very important, you know, for the simulation process, these material data.
Yeah, generally speaking, when we talk about material characterization for something that is a structural analysis, from general point of view, I always suggest to be, let's say, present before at all to the experimental test. That is always a good thing. And in terms of simulation, Jeff has already told about, speak about during its presentation. I always suggest to, let's say, to start to make a start point with our multi-scale environment. It can be used to put together fiber and matrix behavior in order to get its global behavior. And this can be a good support for the static analysis, for instance, in order to have some good admissible for failure criteria in OptiStrat, for instance, or maybe for dynamic analysis when we can catch the correct plastic behavior, for instance, in plane shear test. This is always needed for crash analysis and similar. And this can be used also in order to drastically reduce the number of experimental tests needed. And at the end, if you want to go further, you can also link the material generated by our multi-scale environment directly to our software in order to get in real time fiber and matrix behavior. So this is more or less in 2 minutes.
Thank you very much for your answer. Yeah, this material data is key for simulation and predictivity. And maybe a question for Alessandro regarding then the composite workflow for non-unit directional composites. How can it work with this workflow with Altair?
Yeah, with our tool, we can model several types of composite materials. For instance, we can easily handle woven fabrics, maybe playing with material engineering constant, or as my colleagues said before, using a multi-scale approach. Why not? Other possibilities, I think, is to model also honeycomb structure, for instance, both with a bidimensional, three-dimensional approach or an hybrid approach. So, in short, I think that Altair Suite is full of possibilities in these terms, and it's able to handle easily, let me say, non-conventional composites, or also characterize new material properties, starting from the unit cell with a multi-scale approach or with a larger scale. Finally, I think also that a strong plus for us is the composite optimization technology. So this process is so robust to handle all these type of different possibilities in composites in the composite world. So we are very strong in this also non-conventional approach, I think.
Okay, thank you very much, Alessandro. Then I think we're almost finished. The time is 2:30. If anyone has a final comment, would like to share with the JEC composite community, or to say something at the end. No, that's fine. No, I think it's. I would like to thank you all for participating in this round table, for your comments, the trends, your ideas, and your suggestions. So thank you very much for this. And I would say that if you want to pursue this discussion, there's a lounge also, and there's the virtual booth of Altair that you can ask technical questions. So special thanks to Nerea and to Martin for their participation today and for your talk. And I wish you a very good day. And thank you to the Altair experts that also contributed. Thank you very much, and have a good day.
Thank you to you.
Bye-bye.
Thank you. Goodbye.
Bye. Bye.
Bye.